Good morning. Welcome in lecture number 2 of pavement design and analysis. Is maybe you already learned from the tutorial number 1 about that how we can resolve or solve the basic pavement design if we have a one layer system. In that specific lecture, we will mainly talk about the conceptual background of two layer system. We will also try to compare it with the two layer system with one layer system, that why we moved, why the designer moved from one layer to two layer system, and I will also give you a brief introduction about three layer system as well. Coming to our topic, the two layer system were basically determined for the purpose again to define or to derive the stresses, strain, and deflection in the flexible as well as in the rigid pavement. The assumption were quite different as compared to one layer system, which we will discuss in the next slide, but keep in mind few things which should be keep in mind. The very first difference between one layer and two layer system, that loading pattern were completely considered as a UCLA, uniformly circular loaded area. Okay, so like uniformly load were acting from the top, which is exactly the exact representation of the wheel load. The second thing was the second main assumption which were considered was that all the materials in like each layer are homogeneous, isotropic, and elastic. So like Hooke's law is also applied on that, while the material have the same properties in the each layer. Okay. The third thing was that the depth is finite. That means is you can see in that figure that h1 is basically like define or like determine, while in the one layer system we have the infinite depth, and also the z value, which is basically depth, or which we call the, if we for example want to determine the depth or the vertical stresses or like deflection at any interface or offset. While the third one is both layer, like the one which is base course and the one which is a subgrade, so like E1 and 2, both layer were basically connected. So that means that the two layer system is a bonded system. Okay, is not unbonded system. The main also unique point in two layer system is it's basically dependent on the Young modulus. So like E1 and E2 is basically the Young modulus of each and every layer. Okay, while the fourth one is in that specific system we can also determine all those parameters at surface as well as in the interface as well. So the two layer system gave us little bit more freedom as compared. As you can see here, we can also apply the same method on the flexible as well as on the rigid pavement. As you can see here, we have the factor which is below is E2. E2 is basically the factor of a Young modulus of the supporting layer. So keep in mind, if we want to determine the deflection at any layer, okay, so it's possible, but E2 we usually use is a the layer which is basically below the like base course, which is a subgrade layer. Okay, and according to also that layer, we also consider that specific theory also consider that stresses at surface and stresses at top of the subgrade are basically also equal in the ratio as well. So like we will have the same stresses at surface as well as at the subgrade level. If you want to compare both system, one layer and two layer system, is you can see here at the left side we have a one layer system, where the first difference was that we can that one layer system consider the load is a point load, but in a two layer system it considered a load is a circular cyclic loading. Okay, the second was that it also assumed that all the material below pavement is homogeneous, subgrade, and elastic, which is also the kind of a same parameter here as well. As I mentioned in the previous lecture, that basically one layer, two layer, and three layer system, they they have almost similarity, but the loading condition and also to determine different parameters, so it gave us little bit more extendable version from 1 layer, 2 layer, and 3 layer, and so on. But the main difference between both of them was the loading parameter consideration, and also the two-layer system enable the designer to determine the stresses, strain, deflection at surface as well as at the interface as well. This is the one typical diagram which we will use to determine the vertical surface deflection. For that purpose, we will have a few parameters, as you can see here on the right side. When we want to determine the f value for the deflection equation, so we have already deflection equation, so all the parameters will already be given. So we need to multiply that parameter with 1.5 into QA. QA is basically the loading category, and E2 is basically the Young modulus of the supporting layer. While the basic purpose of this chart is we need to determine the F2 value from that very specific figure. For that purpose, we need E1 and E2, means Young modulus of the both layer, as well as we need the height and radius of the cyclic loading. So then we can determine the F value from that specific chart. As you can see here, this is our very first example. Okay, we are trying to determine the suitability, and we want to compare it the thickness which we provided 12 centimeter, is it acceptable or not. So we have a cyclic loading of 80 psi, okay, and the radius in both sides from where the force is basically acting is 6 inches. Okay, the tire pressure is also given, while we have the elasticity of the pavement material at the base course level is also given, as well as at the subgrade level is also given. So what we will do, the very first step, we need to determine the according to that specific chart, the h1 by a. So h1 is already given is 6 inches, while a is also given, so it comes 1. And we want to determine the Young modulus comparison as well from E1 and E2 figure. Okay, so it's come like 50,000 psi divided by 10,000, which is almost equal to 5,000 psi. Okay, so from that specific figure, we will consider all those parameters, as you can see here. So the question is how to select. So now first of all, we will go for the value of h1 by a. So as you can see here at the below, we have a graph starting from 0, 0.5, 1, 1.5, 2, 3, 4, and so on. Similarly, at the another side, we have the value of E1 and E2. So from here, we will select the specific curve, the specific line where we have the value of that is 5. So we will select we will actually select the point of h1 by a and e1 by e2, where both lines are basically intersecting with each other. So the f2 value is somehow 0.6 or 0.59. So we consider here the value of f2 is 0.6. So this is the way how we should select the value of the vertical surface deflection for the two-layer system. So we just put it in that specific equation, so we determine the level of deflection. Okay, coming to that another example. Now we would like to determine the, as I mentioned that in the two-layer gave us little bit more freedom as compared to one layer, so we can also determine the deflection value at the interface as well. Okay, so we have a similarly loading is also given. We have the Young modulus of the both layer, we have the thickness as well. So what we have to this is another graph through which we determine the vertical deflection at any point which need to be you want to determine. So we have the three basic parameter. The first one is the offset, which we determine with r by a. So we don't have any radial point. Okay, so we have a, but we don't have r because we don't want to determine it below any point. So in that specific condition, we consider r by a is equal to 0, while the e1 by e2 is equal to 5, while h1 by a which is 12 divided by 12, which is equal to 1. So what we do, we gonna go with the E1 and E2, which is equal to 5. So we consider the value of 5 from all those lines, and then we also consider the offset r by a is exactly is equal to 0, and we also consider from here the h1 by a, which is exactly at your left side. So from here we will intersect exactly all those points, which is almost equal to 0.80 or is equal to 0.83 or 84 or 85. So we put that value and we got our deflection at interface level. Okay. Similarly, the same example is basically repeated just to give you idea. Okay, so like for example, you can also change all those parameters as well. Okay, so you can come up with something like, for example, you can change the value of the height of the thickness of the each depth, and you can also determine your own deflection as well at any point. We have another example where we would like to check the suitability of 24 centimeter thick flexible pavement. According to the two-layer system, the pavement has carry a wheel load of 40 kilonewton, which exert a tire pressure of 0.5 on the pavement surface. So modulus of elasticity for the material as well as for the subgrade is already given. So first of all, we have the given data which we already mentioned here. So I would just give you one hint to go in a very detail. The deflection should be less than 5 millimeter. It means that we would like to allow the maximum deflection of 5 millimeter, which is again recoverable, is according to the pavement definition that the pavement is alive, it can contract and it can come back to its original position. Okay, expand and contract. So far we through the thermal crack system, so far from the practical analysis, we have determined that at maximum level, when the temperature crosses like around 60 to 70 degree, maximum 28 millimeter deflection or like the expansion of those joints are actually considered or like counted. But in that design parameter, in the theoretical approach, we will assume it a 5 millimeter. Okay, what we will do, first of all, we need to determine the circular contact area. So area is equal to wheel load divided by pi into the pressure, okay, which is already given. Wheel load we have already, so we just need to put our parameters there. Okay, so we have the radial circle of the the circle radius area, which is equal to 16 centimeter. We also determine the E1 by E2 value as well for the graph purpose. So we have a formula 1.5 PCA into F divided by E2. So we have PC value is already there, A is already determined, which is 16 centimeter. E2 is also already like given, the subgrade material, the subgrade Young modulus. So what we gonna do, we gonna check the F2 value from that specific figure, okay, which is already mentioned in the below. So while putting all those figures together, we have the value of 1.92 millimeter, which is exactly less than 5 millimeter. So that means that this is our edoxy or the suitability that we would like to check that either 24 centimeter thickness is enough or not. Okay, so this is a kind of a parameter check which you need to keep in mind. Welcome in the three-layer system. So now when we have a problem or the addition of the one layer to the two layer, so when the two-layer system have some drawbacks, so then we move to the three-layer system. Okay, the three-layer system were basically wasn't applicable anymore. So the same the same scientist Boussineas and Burmister, they basically develop the three-layer system as well. Okay, and they considered that all the material in each layer is homogeneous. Of course, the load were also considered as a circular cyclic loading. Okay, and then we have the layer 1 and layer 2 have the finite or the confined thickness, okay, but they are basically infinite in the x-axis direction, while of course layer 3 it have infinite, because we are here dealing with the subgrade and you cannot determine the subgrade below the natural level and load distribute over a circular contact area. From this specific chart you can see here, if we talk about layer 1, layer 2 and layer 3. So what is basically H? H is the thickness. What is E? E is Young modulus. Okay, so now for the very first thing we would like to see the contact area between the tire and the wearing course, which we determine with ZZ0. Okay, and then we have the vertical stresses at the very first interface. Interface means the layer below like above the layer 2 but below the layer 1. So this is our interface, like in the middle. Okay, so we determine that value with ZZ1. Similarly, if we would like to determine the horizontal stresses at the base of the top layer, we determine it with RR1. Similarly, if we would like to determine the horizontal stresses at the top of middle layer of the second layer, so then we will have the value of RR2. And if we would like to determine the horizontal stresses at the base or middle layer, so then we come up with RR2 or RR2 2 dash. Okay, and then similarly we can also determine the vertical stresses at the second layer interface as well, which is ZZ2. And then at the end you can also determine the horizontal stresses at the top layer as well. Okay, but of course we will not have the vertical stresses at the lower layer. Okay, so we because vertical stresses will only act in the layer 1 n as well as in the layer 2. Okay.